Welcome to our journey into the world of atoms. Atoms are the fundamental building blocks of all matter, and understanding their structure is key to unlocking the mysteries of chemistry and physics. Today we'll focus on one of the most important aspects of atomic structure, electronic configuration. This concept explains how electrons are arranged around the nucleus of an atom, influencing everything from chemical reactions to the properties of material. Let's start by exploring what makes up an atom and why the arrangement of electrons is so crucial. Electronic configuration refers to the specific arrangement of electrons in an atom's electron shells and subshells. Each atom has a unique configuration that determines its chemical behavior. By understanding electronic configuration, we can predict how atoms will interact, bond, and form compounds. This concept is foundational in chemistry, helping us explain why sodium reacts explosively with water or why noble gases are so unreactive. Let's dive deeper into how electrons are organized within an atom. Atoms consist of a central nucleus, made up of protons and neutrons surrounded by electrons. These electrons don't just float randomly, they occupy specific energy levels or shells. Each shell can hold a certain number of electrons, and the way these electrons fill the shells follows a set of rules. Understanding this structure is essential for grasping electronic configuration, as it sets the stage for how electrons are distributed. Electrons in an atom are arranged in energy levels, also known as shells. These shells are labeled as K, L, M, N, and so on, starting from the one closest to the nucleus. Each shell can hold a maximum number of electrons. The first shell holds up to 2, the second up to 8, the third up to 18, and so forth. The arrangement of electrons in these shells is not random but follows specific principles that we'll explore next. Aufbau principle is a key rule in determining electronic configuration. It states that electrons fill the lowest available energy levels first before moving to higher ones. This means that electrons will occupy the 1's orbital before the 2's, then the 2p, and so on. This principle helps us predict the order in which electrons fill the various shells and subshells, ensuring the atom remains as stable as possible. Another important rule is the Pauli exclusion principle. This principle states that no two electrons in the same atom can have identical quantum numbers. In simpler terms, each orbital can hold a maximum of 2 electrons, and they must have opposite spins. This rule ensures that electrons are distributed in a way that minimizes repulsion and maximizes stability within the atom. Hund's rule is another guideline for electron arrangement. It states that electrons will fill degenerate orbitals of the same energy singly before pairing up. This minimizes electron repulsion and leads to a more stable configuration. For example, in the p subshell, each of the 3 p orbitals will get 1 electron before any pairing occurs. This rule helps explain the magnetic properties of certain elements. Quantum numbers are used to describe the unique position and energy of each electron in an atom. There are 4 quantum numbers: principal, angular momentum, magnetic, and spin. These numbers help us specify exactly where an electron is likely to be found and how it behaves. Understanding quantum numbers is essential for writing accurate electronic configurations. Principal quantum number, represented by n, indicates the main energy level or shell that an electron occupies. The value of n can be 1, 2, 3, and so on, with higher numbers corresponding to shells further from the nucleus. This number plays a crucial role in determining the energy and distance of the electron from the nucleus. Angular momentum quantum number, L, defines the shape of the orbital where the electron resides. It can have values from 0 up to n1. For example, if n equals 2, L can be 0 or 1, corresponding to s and p orbitals. This quantum number helps us understand the geometry of electron clouds around the nucleus. Magnetic quantum number, ml, specifies the orientation of the orbital in space. For each value of L, ml can range from L to plus L. This means that for p orbitals L equals 1, ml can be -1, 0, or +1, representing the 3 possible orientations of p orbitals. This quantum number is essential for understanding how electrons are distributed in 3-dimensional space. Spin quantum number, ms, describes the direction of the electron's spin, which can be either +1, 2 or -1, 2. This property is crucial because it allows 2 electrons to occupy the same orbital as long as they have opposite spins. The concept of electron spin is fundamental to the Pauli exclusion principle and the overall arrangement of electrons. Orbitals are regions within an atom where electrons are most likely to be found. Each shell contains 1 or more subshells labeled S, P, D, and each subshell has a specific number of orbitals. S has 1, P has 3, D has 5, and F has 7. The arrangement of electrons in these orbitals forms the basis of electronic configuration. Electrons fill orbitals in a specific order, starting with the lowest energy level. The general sequence is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. This order is determined by the relative energies of the orbitals, which sometimes means that a higher shell fills before a lower one. Understanding this sequence is vital for writing correct electronic configurations. To write an electronic configuration, we list the occupied orbitals in order of increasing energy, indicating the number of electrons in each with a superscript. For example, hydrogen's configuration is 1s 1, while carbon is 1s 2 2s 2 2 p2. This notation provides a quick way to visualize how electrons are distributed in an atom. Noble gas notation is a shorthand way to write electronic configurations. Instead of listing all the filled orbitals, we use the symbol of the nearest noble gas in brackets, followed by the remaining configuration. For example, sodium's configuration is Ne3s1. This method simplifies configurations for larger atoms. Let's look at hydrogen, the simplest atom. It has one electron which occupies the lowest energy orbital 1s, so its electronic configuration is simply 1s1. This straightforward example sets the stage for understanding more complex atoms. Helium has 2 electrons, both of which fill the 1s orbital. Its electronic configuration is 1s2. With a full first shell, helium is very stable and unreactive, which is why it's classified as a noble gas. Lithium has 3 electrons. The first 2 fill the 1s orbital and the third goes into the 2s orbital. Its configuration is 1s2-2s1. This arrangement explains lithium's chemical reactivity and its position in the periodic table. Carbon has 6 electrons. Its configuration is 1s2-2s2-2p2. The distribution of electrons in the 2p orbitals allows carbon to form 4 covalent bonds, making it the backbone of organic chemistry. Neon has 10 electrons, filling the 1s, 2s, and 2p orbitals. 1s, 2s, 2p6 with a completely filled outer shell. Neon is extremely stable and does not react easily with other elements. Transition metals have more complex electronic configurations due to the filling of d orbitals. For example, iron has the configuration R4s 2,3d6. The presence of partially filled d orbitals gives transition metals unique properties, such as variable oxidation states and magnetic behavior. Lanthanides and actinides are 2 series of elements with electrons filling the f orbitals. These elements have complex configurations and are often placed separately at the bottom of the periodic table. Their unique electron arrangements lead to interesting chemical and physical properties. Some elements have electronic configurations that don't follow the expected order. For example, chromium and copper have unusual arrangements due to the extra stability of half-filled and fully filled d subshells. These exceptions highlight the complexity and nuance of electronic configuration. Valence electrons are the outermost electrons in an atom and play a key role in chemical bonding. The number of valence electrons determines an element's reactivity and the types of bonds it can form. Understanding electronic configuration helps us identify valence electrons quickly. The Octet rule states that atoms tend to gain, lose, or share electrons to achieve a full set of 8 valence electrons. This rule explains the stability of noble gases and the common bonding patterns seen in other elements. Electronic configuration is the foundation for understanding the Octet rule. Electronic configuration helps explain trends in the periodic table such as atomic size, ionization energy, and electronegativity. As you move across a period or down a group, the arrangement of electrons changes in predictable ways, influencing the properties of elements. Atomic size or atomic radius is influenced by electronic configuration. As electrons are added to the same shell across a period, the nucleus pulls them closer, reducing atomic size. Down a group, new shells are added, increasing atomic size. This trend is a direct result of how electrons are arranged. Ionization energy is the energy required to remove an electron from an atom. Elements with stable electronic configurations like noble gases have high ionization energies. Those with only one valence electron, like alkali metals, have low ionization energies. This property is closely tied to electronic configuration. Electronegativity measures an atom's ability to attract electrons in a bond. Elements with nearly full valence shells, like fluorine, have high electronegativity. Those with few valence electrons, like sodium, have low electronegativity. Electronic configuration helps us understand these differences. The way atoms bond is determined by their electronic configurations. Atoms will share, gain, or lose electrons to achieve stable configurations, often following the Octet rule. This leads to the formation of ionic, covalent, or metallic bonds, each with distinct properties. When atoms gain or lose electrons, they become ions. The electronic configuration of ions differs from their neutral atoms. For example, sodium loses one electron to become Na+ with a configuration like neon. Chlorine gains an electron to become Cl-, also achieving a noble gas configuration. Isoelectronic species are atoms and ions with the same electronic configuration. For example, Na+, Ni, and F- all have the configuration 1s 2s 2p6. Recognizing isoelectronic species helps in understanding chemical behavior and trends across the periodic table. The magnetic properties of an element depend on its electronic configuration. Atoms with unpaired electrons are paramagnetic and attracted to magnetic fields, while those with all electrons paired are diamagnetic and slightly repelled. This distinction is important in both chemistry and physics. When electrons move between energy levels, they absorb or emit energy as light. This process produces spectral lines which are unique to each element. By studying these lines, scientists can determine the electronic configuration of atoms and identify elements in stars and distant galaxies. The quantum mechanical model of the atom provides a more accurate picture of electronic configuration than earlier models. It describes electrons as existing in probability clouds or orbitals rather than fixed paths. This model explains the complex arrangements and behaviors of electrons in atoms. concept of electronic configuration has evolved over time. Early models like Bohr's depicted electrons in fixed orbits. Later, quantum mechanics introduced the idea of orbitals and probability, leading to our current understanding. This evolution reflects the progress of scientific discovery. Electronic configuration is essential in many areas of chemistry. It helps explain the periodic table, predict chemical reactions, and design new materials. Chemists use this knowledge to create everything from medicines to advanced electronics, making electronic configuration a cornerstone of modern science. In physics, electronic configuration explains phenomena like conductivity, magnetism, and the behavior of semiconductors. Understanding how electrons are arranged allows physicists to develop new technologies and materials, from superconductors to quantum computers. Even in biology, electronic configuration plays a role. The behavior of atoms in biological molecules such as proteins and DNA depends on their electron arrangements. This understanding is crucial for fields like biochemistry and molecular biology. Current research in chemistry and physics often focuses on manipulating electronic configurations to create new materials with unique properties. From superconductors to nanotechnology, understanding and controlling electron arrangements is at the forefront of scientific innovation. Common misconception is that electrons orbit the nucleus like planets around the Sun. In reality, electrons exist in probability clouds called orbitals. Another misconception is that all elements strictly follow the filling order, but as we've seen, there are exceptions. Understanding these nuances is key to mastering electronic configuration. To solidify your understanding, it's helpful to practice writing electronic configurations for various elements. Start with simple atoms like hydrogen and helium, then move to more complex ones like iron or krypton. Practice helps reinforce the rules and exceptions we've discussed. Let's recap what we've learned. Electronic configuration describes how electrons are arranged in atoms following specific rules and principles. This arrangement determines an element's chemical and physical properties, influences trends in the periodic table, and underpins much of modern science. Mastery of this topic opens doors to deeper understanding in chemistry, physics, and beyond. As we continue to explore the world of atoms and molecules, electronic configuration will remain a central concept. Whether you're studying chemistry, physics, or biology, understanding how electrons are arranged will help you unlock new discoveries and appreciate the complexity of the universe. Stay curious and keep learning.